Hi and welcome back to a new video. Today is finally the time that we can talk about Intel Arrow Lake, at least the official Intel slides and technical specs, some details about performance, but only the part that Intel published themselves. So only in about 2 weeks there will be the independent reviews, such as mine, and then we can talk about independent review and performance testing. But still, there are a lot of interesting facts about Intel Arrow Lake specs, how the CPU is made, and like socket details, performance, and that's what we'll talk about in today's video. You surely saw the Seasonic MagFlow fans in one of my videos before. Seasonic also offers them in an ARGB version. With a different fan blade design, RGB inside the frame and also subtle RGB in the center, these fans focus on both design and performance. The MagFlow ARGB are also daisy chainable and can easily be expanded and connected by the integrated magnets that couple the fans without additional clips or tools. Seasonic also includes a small RGB controller if you want to avoid annoying software issues. Find out more in the link below. The new generation, as you probably already know, is not the 15th gen, it's now called Intel Core Ultra 9 285K. I already, in a German live stream was talking about what I think about the Ultra naming scheme. I'm not a big fan. I preferred the i9, i7 stuff, but here we are. Regarding the base spec, the 285K will again feature 8 P cores and 16 E cores, as you can see in this huge overview slide, and the boost clock is set to 5.7 GHz for the 285K. On this slide we see what Intel thinks about Arrow Lake and its goal. They target performance per watt and efficiency heavily, so that's their pure focus, something completely different compared to the 4900K. And compared to the 4900K, the power consumption on average should be 40% lower, which is quite a bit. At the same time, multi-threading performance, so for example Cinebench R23, is supposed to be 15% higher. On the other hand, gaming performance seems to be identical to the 4900K. Another benefit, the temperature is supposed to be 10 degrees Celsius lower than previously. This slide is already quite insane. I think it's cool that Intel targets efficiency and that the power consumption is a lot lower than previously, while they also still were able to increase the multi-threading performance and also drop the temperature, which I think goes hand in hand with the lower power consumption. But then they maintain the same gaming performance. That's what they say. So we're expecting, or we should expect, the same gaming performance as with the 4900K, which can be underwhelming. Still, it could be impressive if the CPU cuts basically the power consumption in half. And this is what we see in a lot of the slides that Intel published. They're all kind of like same performance as Raptor Lake, but basically cut the power consumption in half. According to Intel, the E-cores are now 32% faster and the P-cores performance increased by 9%. The cache also slightly increased in size, and you can now overclock the CPU in steps of 16.6 MHz, which is definitely something cool and useful for overclocking. So Intel highlights that the E-cores improved by 32%, P-cores by 9%, yet they claim that the overall performance in gaming of the 285K and the 4900K should be the same. Why is that the case? For this we take a quick look at this slide. We stay with the 285K. Obviously, if you just want to check out more details, always pause the video and read through the slide if you want to. But the 285K features 8 P cores, 16 E cores, same as the previous gen, and is listed with a max clock of 5.7 GHz. However, that is just the single core boost as usual. And if we look at previous leaks, we know that the all-core boost clock of the CPU is supposed to be between 5.3 and 5.4 GHz across all of the P cores, and that depends on the thermal velocity boost, so the temperature of your CPU. And that means that on average the 285K will have about 6% lower clock than the 4900K, while the 285K has a P core performance increase of 9%. So overall, if you just calculate that, the 285K should be roughly 3% faster in gaming, which is also according to Intel in some slides, basically tolerance. However, good thing, the E-cores drastically improved in performance. So 30% performance uplift, that will lift up the E-cores. Previously, if you look at a 12900K, the E-cores there had a performance of roughly a 6700K. With a 30% performance uplift, those E-cores should now be about as fast as the P-cores of the 12900K. So that is quite interesting and should also explain why the 285K is much stronger in multi-threading, like rendering loads. We are now looking at how the CPU is made. Previously, like the 14900K, was a monolithic die, so a single silicon chip. Now, the CPU consists of 6 individual chiplets. On the bottom, we have the base tile that connects all the chips with each other. On top, you have multiple smaller ones, starting with the GPU tile that includes the integrated XE graphics unit that also is much faster than before. Next to it, we have the SoC tile that contains a bunch of controllers, such as also the memory controller. And then we have the compute tile, probably the most important one, that contains the P and E cores. And next to it, also the I/O tile for the connection. There was also unused space that they call filler tile, so that should be an empty piece of silicon. All of this is very interesting from a technical perspective because it's the first Intel desktop CPU to feature a base tile and multi-tiles on top. There was Meteor Lake, but it was only a mobile CPU. It's also interesting in regard of overclocking and tuning because you will have different buses that are connecting the tiles with each other. So there's a lot of things you can tune when it comes to different multipliers and stuff, but we will feature that once we can talk about performance and also show how this is done in about 2 weeks. Intel is talking a lot about power and power efficiency. For example, here, a landmark reduction in power, and then they also switch over to here where they talk about lighter workloads, and that in lighter workloads compared to the previous gen, it now is a reduction of 58% in power draw. In single-threaded applications, so if you use only one core, the 285K is supposedly 4% faster than the 9950X. And in those single-core applications, on average, it's supposed to be 8% faster than the 14900K. However, back to multithreading, where Intel says it's much faster, the 285K is supposed to be 15% faster than the 14900K and 13% faster than the 9950X. On average, Intel claims that the 285K consumes 73 watt less than the previous 14900K. And all this combined, at least according to Intel, is leading to an average temperature reduction of 13 degrees Celsius over the 14900K. While I can fully understand that Intel always uses the 9950X from AMD as a comparison to the 285K because they're like, the flagship CPUs and at the same time in the similar price range, I'm still missing the 7800X 3D for all the gaming benchmarks because we all know that the 7800X 3D is much faster in gaming than the 9950X. The fact that the 7800X 3D is not listed in any of these charts or comparison probably means that the 285K is slower than the 7800X 3D, at least in gaming. Multi-threading and rendering probably a lot different. There were also a lot of AI advertisement slides and how quick the 285K is with AI, but honestly, I'm not sure if you're interested in that. I'm not, so we will not cover that part. This slide regarding overclocking is quite interesting because, as I said before, Arrow Lake, just because of the way it's made, it's quite complex. You have all those different tiles with all the bus connections in between that can be tweaked and also overclocked. Also, Arrow Lake now allows adjustments of the clock in 16.6 MHz steps. So if you're looking for the highest CPU frequency possible without touching the B clock, it is now much easier than previously. Intel also improved the memory controller to the previous gen, so you can run higher memory speeds, and it now also supports CUDIM. You can clock P cores and E cores individually, which is something that already existed before. And in the center there is something quite interesting, and that is called DLVR bypass, and that's a very interesting detail. Intel Arrow Lake features a DLVR, a digital linear voltage regulator. Previously, if we look at the 14900K, you had your motherboard and the VRM was delivering the core voltage directly to the CPU. Now you have the DLVR in between. So you have an input voltage that is fed from the mainboard VRM to the DLVR, and the DLVR then regulates the voltage to the CPU cores. That allows, for example, tuning of the individual P cores. So each P core can have its own voltage, which is a positive thing. But there are also negative things. That's why the DLVR bypass exists. Can't talk too much about that yet. That's something we will cover in the launch review. I can just tell you that the DLVR topic, basically underrated, and the fact that it's not listed anywhere in the presentation kind of blew my mind, but it's cool, complex, and complicated at the same time. Intel Arrow Lake memory controller also supports a higher frequency, officially 6400 megatransfers, and thus this is the fastest memory controller for desktop CPUs currently. Intel now also, same as AMD previously, supports ECC for the CPUs. Again, we have those up to numbers that don't really help anyone. Really, Intel, next time, same as AMD, if you do those kind of presentations, please make them more clear. It's the same with up to 5.7 gigahertz. Now we have up to 6,400 megatransfers. What does it mean? In which scenario? Because we know it will be different from 1 DPC motherboards to 2 DPC motherboards. And at least from the information that I have right now, the 6400 is only supported if you run CU-DIMM on a 1 DIMM per channel motherboard. If you run normal UDIMM, it's supposedly only 5600. But then it's also 5600 if you run 2 DIMMs on a 4 DIMM board. But if you run 4 DIMMs on a 4 DIMM board, it's supposed to be 4800. But that's not officially confirmed right now. It seems like Intel is also not quite sure what it is officially. I will try to get this information confirmed for the real launch video, but right now, yeah, it's a bit confusing. And talking about confusing things, let's go over to PCI Express lanes, because at least to me, this is another very confusing slide. Bottom left, we see that the platform itself supports a total of 48 PCI Express lanes. On the top right, you can see that 24 of these come from the chipset, so 24 from the chipset. If we do the quick math, we see 48 lanes in total, 24 from the chipset, which equals 24 from the CPU. But there it's where it's getting a little bit more confusing. So if I got this right, also looking at the motherboards I have, then we should have 20 PCIe Gen 5 lanes. So 16 to your graphics card, 5 dedicated to a PCIe Gen 5 NVMe drive, and another 4 Gen 4 for another NVMe drive. At least that's how I kind of tried to get this information together, because it's simply missing and not clearly written on any of those slides. Yeah. We're moving away from all those slides for a second to talk about the C890 Apex from ASUS, also the CPU itself finally, and also the socket, which has some changes to it. Here we have a direct comparison of a 13th gen or 14th gen and the 285K. We first start with some physical properties. Bottom left and bottom, we have 13th and 14th gen, we have those SMDs. On Intel Arrow Lake, it's top left, and bottom right, we have a lot of SMDs. That's just important, especially for the lidding. So if you would want to push the IHS in any single direction, like top, left, right, whatever, it would always permanently damage your CPU. You would always cut off some of those SMDs, which makes the lidding pretty complicated. But we already have a solution for that. We will talk about that once we have the final go on those CPUs. On the previous gen, we had a lot of testing points, so top left, top and bottom on the PCB, also on the right, which are no longer there on the Intel Arrow Lake CPU. If we flip it around, we can first see that this one has more contact pads. That's because we have 1,851 contact pads, whereas previously we had 1,700. But actually it has a bit more, and that's because of the total left row and total right row of Intel Arrow Lake. Because you can also see those are shaped a little bit different. Total left row is round. The center pieces are all like a rectangular shape. Right one, again, round shaped. That's because the left and right row of Intel Arrow Lake are the test pins that were moved down from the previous gen, where it was on the top side. That's what we just talked about. They moved this to the bottom piece of the PCB. So those left and right rows are not really relevant for us to use it, but seems like Intel did some changes here for testing for whatever purpose. You may have also noticed that the IHS shape is different. It became a little bit more narrow, but also longer. It changed from being 38.4 by 28.4 to 39.2 to 25.4. So on this one, we have 996 square millimeters, and on this one, we have 1090 square millimeters. We're talking about a reduction in surface area on Arrow Lake by about 9%. You may now ask, okay, so is this a problem that the IHS is becoming smaller? So less surface area means less contact to the cooler, worse cooling. But at least if we look at all those Intel slides that we just looked at, and if we're talking about cutting the power consumption in half, this should not be a problem. There were rumors that Intel changed the PCB thickness on the 285K to fight bending of the CPU, and that also the different IHS shape is because of this issue, that they tried to change this, or at least kind of fight the problem. So first, we're looking at a 4900K. PCB thickness is about 1.15 millimeters. Intel Arrow Lake is indeed a little bit thicker when it comes to the PCB, 1.19 millimeter. However, we're talking about a difference of 4%. Which shouldn't really help the mechanical stability. Now that we're talking about sockets and bending, I think we can talk about the fact that there are two different sockets now with Intel Arrow Lake or 1851. From the base principle, we still have the ILM that's made from two pieces. So the top one and the piece that pushes it down. So you would put your CPU in there, close it, close the lever, and the notches on left and right are pressing down onto the CPU, which was causing the issues on socket 1700 that the CPUs would bend because they're like rectangular, longer shape, and the pressure is applied in the center. What Intel did to fix this is doing the same socket again. But they now call it the reduced load ILM, the RL-ILM. That's what you can read on here. That's also how you can differentiate between the two different sockets. And what they did is basically a washer mod. I took out this piece of ILM for you, just removed it from here. So you can see what Intel did. They added a thin piece of plastic underneath the socket. And that's what they call the reduced load ILM. So what they did is just elevating this a little bit to reduce the load of the ILM on the CPU. Which to me, is kind of the same thing as you're having a headache and instead of going to the doctor to check what's wrong and actually fix it, you just take an aspirin every single day. That's basically this. Yeah. I don't really understand why they didn't move to what we're doing, like with contact frame stuff or just apply the pressure from the corners. Seems like a strange solution to me. I also saw a slide where they claimed that this fully fixes the issue. If that's really true or not, we can simply test it, put a CPU in the socket, and measure if there's a difference. For this, we will first measure the CPU in the normal socket, then change the same CPU into a motherboard with the reduced load ILM, and then in the end with a contact frame. That is basically the same that we had with the normal socket 1700. We have about 80 micrometer difference from left and right, so the high points to the low points in the center where it's pretty much concave. So now we will check how much the reduced load ILM will help us. The reduced load ILM definitely helps. It didn't quite cut it in half, it didn't fix it for sure, but it helped. So it went from 79 micrometer bending to 45 micrometer in bending. And now with the CPU contact frame, you can see the bending is 36 micrometers, but it's the opposite direction. We now have the high point in the center, which is exactly what we want, that the contact is as close to the center as possible to the hotspot. Yeah, so you can see the reduced load ILM, it helps. We can't talk about the exact cooling numbers yet. That is something for the final video once we can power on and test the CPU, but at least we can see reduced load ILM helps, but it definitely does not fix the bending issue completely. Now that we know that it helped, but it didn't fully fix the issue, I'm pretty sure a lot of people will still want to use their contact frames, maybe reuse the 1700 ones or get a new one. For reusing the 1700 one, it could be difficult. First of all, there is this notch right here on the bottom that was not present on 1700. So this could potentially collide with a lot of existing 1700 contact frames, make it not compatible. Then they also shifted the socket by about 1 millimeter to the south. You can easily see that if you compare the distance between this hole and the edge and this hole and the edge. You can see this is a little bit wider. You will know from the slides that we just looked at how the CPU is built internally with all those different tiles. And the compute tile that contains the P&E cores is sitting somewhere here, so it's a little bit further north of the CPU. That's why Intel decided to push the CPU as far north as they can without conflicting anything with the socket and cooler mountings. So they changed it to move it a little bit downwards by about 1 millimeter, so the CPU sits closer to the hotspot of the cooler. That is beneficial for cooling. That's a good thing. But it just means that a lot of probably existing contact frames are no longer compatible because they won't align anymore with the existing holes. That's the same problem that we are facing with the 1700 contact frame. So we had to make the new one that I already showed you, where we saw the good temperature gains or like the bending gains. I can't talk about temperature yet, obviously, but you could see that it changes. It completely changes how the CPU is bent from being concave in the center to be convex in the center. I also ordered one of those China frames from Amazon just to double check the compatibility for you, because I know that a lot of people used them previously on 1700 and are maybe thinking to reuse it for 1851, but as expected, because of the socket shift, it won't fit. You can see it right here, because the socket is shifted towards that direction, so you can't mount it down anymore. Apart from the fact that it wouldn't make too much sense anyway. You can see the IHS is just more narrow, so cutout is too wide, so yeah, it won't be optimal. Probably wouldn't really help anyway if like the cutout is in the wrong dimension. So yeah, if you have one of those contact frames similar to that, same goes for the Grizzly 1700 contact frame. The previous ones won't fit on 1851. And before we end this video, there is one more important detail, and I'm not sure if this is just exclusive for ASUS motherboards, because I don't have my MSI and Gigabyte boards yet. But previously, if you wanted to measure CPU power consumption, you would always just measure EPS power from those two 8-pin connectors. But now, this portion right here is powered by 24-pin ATX and also by this on the bottom. That is mainly because they had to run PCIe lanes through here, and it would interfere with the power supply of these VRMs. So they had to split it up. But for any kind of monitoring, reviewing, this can be a challenge, because a lot of reviewers, at least from my knowledge, are tracking power from just the 8-pin EPS connector. And if you're doing that right now, you will get reported a lot lower values than what the CPU realistically will have. And it's no longer that easy, because if you want to measure this one, it will also include like M.2 power consumption and graphics card power consumption as well from the slot. That's why, yeah, tracking power consumption of Arrow Lake just through the connectors is not that easy anymore. Pricing wise, the 285K is listed with an MSRP of $589. It will now depend on your region, especially if you're outside the US, if there's like maybe VAT added or currency conversion. That will be something you have to check locally, but at least what I can judge here in Germany, it should be slightly cheaper than the 9950X from AMD. And according to the slides from Intel, it should beat the 9950X in a lot of multi-threading applications. So maybe in that regard, it makes sense to get the 285K. In gaming, we will see, probably not. At this point, we don't have independent reviews and benchmarks, so we can only talk about what Intel provided or also what they didn't provide. So for example, we know that in not a single slide they mentioned the 7800X 3D. So I would assume that it's pretty safe to say that the 285K will not beat the 7800X 3D in gaming. Otherwise, they would have advertised it, right? On the other hand, it seems like the 285K is a very efficient and very high-performing CPU for any multi-threading workload, like rendering, workstation applications. It seems to be a very good CPU because it increased a lot in multi-threading performance while cutting the power consumption in half. From my perspective, at least, that's quite impressive. I just wish they were still able to increase the gaming performance a little bit over the 4900K. That seems to be a bit of a bummer. Like, yeah, there's a little bit missing. So it's not probably the hype that some people expected, but I think it is a step in the right direction. Let me know what you think about the 285K. Thanks for tuning in. Till next time. Bye.